So our next talk will be by Heather Gaya, and she is going to be presenting a Bayesian hierarchical model to account for bias in Gopher tortoise distance sampling.
So hi everyone. So as mentioned, my name is Heather Gaya and I'm a master's student at the University of Georgia. And I would just, before I start, I'd like to give a shout out to my co-authors, Brian Noose and Dr. Clinton Moore, who have helped me tremendously on this model. And this is much more interesting than the title suggests. So Gopher tortoise surveys, I'm sure we're all pretty familiar with them, but I'm going to go over them again for anyone who's not. They use line transect distance sampling. So this is essentially random transects out in the field. You look to the left and right, you try and find what you find. And typically this is done with 3 observers, but there's some variation depending on the amount of funding you have or the state that you're in and doing the survey. So when you find a burrow, you GPS its location, you measure how large it is, you record some various characteristics about it, and then you might want to scope it for occupancy depending on if you're interested in the burrows or the tortoises. And typically the DNR, when they use this data, and I think most of people who are doing this analysis, they only use occupied burrows. So this requires that you actually find a large number of tortoises in order to get a good idea of the data that's going on. And you need about 60 to 80 tortoises minimum, which is actually quite a lot if you're surveying a very small portion of land or you're surveying a very low density tortoise population. So when we look at the size distributions of these burrows that we collect, so this is the raw data that we get out of line transect distance sampling, we see that there's sort of this, a little laser, we see that there's sort of this gap in these lower burrow widths that we're seeing, like below 20 centimeters wide. We really are seeing these sort of lack of detections, and we're not sure if that's because the tortoises are not reproducing, which would be a concern, or because we're just sort of bad at detecting them. And we'd like some way of like piecing this apart, because this takes about 10 to 15 years of tortoises growing before they can be detected sort of consistently on these surveys, and obviously that's a long time to wait if you're doing any sort of like habitat management and you want to know if the population is crashing. That might be too late to wait. So we wanted to create some sort of model that could look at the data that we already have collected without adding any new information in, and consider how what characteristics of the burrow might be affecting our detection and sort of account for that so that we can get better density estimates and also understand the true size distributions of these populations so we can monitor reproduction. So we have some data based on these 26 enhanced line transect distance survey sampling, and this is essentially just normal line transect distance sampling, but we also have intensive searches. So that way we know what we found with the line transect, and then we went back and did intensive searches in certain areas, so we have an idea of what we missed as well. And then we also have 5 surveys from doing a survey before a burn, and then burning, and then doing a survey afterward. And this model, I should say, does not include vegetation, because that's not something we currently record when we do these surveys. But of course, it is something that's going to be affecting detection. So we wanted to, first of all, consider the size of the burrow, the detection on the transect line, because one of the assumptions of line transect distance sampling is that you have 100% detection on the line. But anybody who's done this knows that that is not true for baby tortoises, that it's very hard to find a tortoise this small when there's any sort of plant, which does happen in nature, unfortunately. Then we also wanted to know if occupancy or activity status, which are other characteristics that are recorded, if those are affecting detection as well. So when we look at burrows that we found versus burrows that we missed, you can see that there's this really unfortunate bar right here of all of these babies that we missed, and we're missing them we're much more likely to miss a baby tortoise than we are to miss an adult tortoise. Really, there's no big difference in the subadult class, which is kind of interesting. But you can see that this says that yes, the probability isn't that a lot of them aren't reproducing. It's probably likely that given that they're there, that we're just missing them. When we look at detection on the line, and then again, there's going to be some variation because of vegetation, which we're not considering here. But you can see that at the lowest size, so about like 5 centimeters wide, that somewhere between 0 and 60% detection on the line. And generally, it's probably going to fall more in this like 20 to 40% range, depending on the habitat you're in. And then it takes for a burrow to get about to like 22 centimeters to maybe all the way up to 27 centimeters before you can actually detect it 100% of the time on the line. So if you imagine how much we're missing and how much that's biasing our normal models that assume 100% detection for all sizes. We were pleased to see that occupancy really doesn't seem to make a difference in whether or not we missed it or not. There's kind of a pretty much an equal number, occupied, unoccupied, depending on whether or not we found it with line transects or intensive searching. But we did see that occupancy does seem to depend partially on size. So we found that the smaller burrows are more likely to be occupied than the larger burrows. And this makes sense based on what we know about tortoise ecology. So we wanted to model that as some sort of negative relationship with size. But it's not obviously that strong, and this is obviously going to depend somewhat on the size characteristics and like detection and a whole lot of other factors. But there does seem to be some general negative relationship going on here. And then again, we looked at active burrows, and this is sort of surprising, but there really isn't any difference in detection between active or inactive burrows. So this isn't collapsed burrows because those don't really look like tortoise burrows anymore. But this is just if you go up to a burrow and you're like, do I think a tortoise is in there? That doesn't seem to really affect whether or not you can find the burrow easily. So then I decided to simplify our Bayesian model for everyone. But if you're interested in the actual mechanics of this model, I'm happy to go over with it later. But essentially, we are taking the information that's already collected from models, so the distance of every object from the transect line, the burrow size, and then some estimate of detection on the line, that probability. We put it into our model, and out pops burrow density, as well as an adjusted distribution of the burrow sizes. So not just taking the raw data, but adjusting for that bias towards the larger sizes and getting an idea of the true distribution of burrows on the landscape. We can then look at occupancy and get the tortoise density and the tortoise distribution size as well. So in order to test how well this model was going to work, we first started with simulation. So even though none of these scenarios are probably likely to be what the true distribution of tortoises looks like out there, we just wanted to know how our model would perform at various extremes. So scenario A is this negative linear relationship. Maybe there are a ton of babies and no adults. Scenario B is this sort of peak for smaller sizes and then another peak for larger sizes. Scenario M is this multimodal, and then scenario U is just a uniform. There's an equal number of babies and adults everywhere. I should say that we modeled this at 4 different densities, 1, 2, 4, and 6 individuals per hectare. So that's kind of giving us sample sizes ranging from about like 20 to 30 individuals at our lowest level up to 150 individuals. And if we remember that the normal way that we do line transects is that we require about 60 to 80 tortoises, so we wanted to see if we could kind of reduce that sample size that's necessary in order to get a good idea of the density of the population. Maybe we can deal with smaller numbers here. So when we look at the relative bias of the point estimates, this is just the point estimate of density out in the landscape. The black model here is our new bias adjusted model, and then the gray is program distance. So you can see, just to kind of orient you, if the point is at 0, that means that we were accurate, that we estimated that our model said this is the density, and that was the true density in our estimated landscape, in our simulated landscape. And then above it means it was an overestimate, and below it is an underestimate. And then this is at 1, 2, 4, and 6 individuals per hectare. And then this is the negative linear, the bimodal, and the uniform distribution. And you can see that for all of these different scenarios that our model either did better or as well as program distance. And so it should also tell you some concerning things that if you're using program distance and you do have some of these distributions, that it's actually giving you some pretty inaccurate estimates. So we were pretty pleased with the results from this. We then looked at the confidence and credible intervals. And so essentially, if you might have the point estimate might be a little bit off, but you would like that interval that it estimates to have the truth somewhere in it. That's kind of the point of a confidence interval. And so you can just see that our model, again, is this one in black, and the program distance is down here. And just at these lower sample sizes, you can see just how poorly program distance performs, and then you can see comparative how nice our model performs. So we were really pretty pleased with that. And then finally, we looked at the size distributions. And so this is estimating what percent of the population is in those smallest 20% of those covariate values, like how many tortoises are there that are under 20 centimeters, might be below reproductive age. And we can see that the true distribution in our simulated set is right here. This nice full bar is the one from our model, and then this raw data is down here. And so at lower sample sizes, even so this is only working with like 30 or 40 individuals, our model was able to fairly consistently estimate the true percentage of those smaller values. And you can see that when we get up to these very large sample sizes, just how far off this raw data is from the truth. And that should just give you some concerns about how detection is coming into play when we're looking at these raw distributions. And so then you might be wondering how this looks in an actual data set. So we took 3 different surveys that the Georgia Department of Natural Resources has done in the past 5 years. And we just ran our model, and we also ran program distance. And so program distance is what they would be using right now to sort of manage these landscapes and determine these populations. So you can see kind of there are about 3 things that you should see here. The first is that our model always estimates that there will be more tortoises than program distance is saying. We also have much more precise estimates. So, somewhere between 0.6 and 2.1 is a very large range of densities, especially when you convert that into abundance, whereas ours is a much more smaller interval there. And then also the CV, which is the coefficient of variation. When you're looking at these surveys, ours also sort of cuts that in half when we look at these surveys. So we were pretty hopeful with this, and it seems like maybe, especially with parts that have lower, especially sites that have lower densities, or you don't have as much field effort is available, maybe you are low on time or resources, we're pretty hopeful that this could be potentially useful. Sorry. And then when we look at the size distribution, so the black line is the raw data that the DNR collected during their survey. So this is burrows, and then we move over to tortoises over here. And then this dotted line is the estimate that our model produces. And you can see that it generally always says that there probably should be slightly more smaller sized tortoises than we predicted, and that there should be slightly fewer of those large sized tortoises than predicted. And I should mention that part of this is you do have to sort of estimate that detection on the line, and that's information that we don't really know. We kind of have to use some sort of prior information or expert opinion or similar. And so this is probably a very conservative estimate that if you assumed that detection on the line, so we were like, maybe detection on the line is like 60% at these sites, but if you remember that graph, it could actually be substantially lower. And so if it is lower than these, we would expect that there would be probably more of these smaller burrows. So this is sort of a conservative estimate. But and so just to kind of summarize all of that, as they say in statistics, all models are wrong, but some models are useful. So we know that this is sort of just an estimation. And we also know that it would be ideal if we could just find those baby tortoises better in the first place rather than having to adjust for it with math on the back end. But this is a good way for us to take data that we already have collected and sort of use it to sort of adjust for those size biases that we're seeing. It seems that our model is able to produce a more accurate density estimate with this updated size information. And we're hoping that we could expand this to other species as well. That might not be as much interest to the gopher tortoise community, but we hope that this would be useful in general just for updating line transect distance sampling for anybody doing these sort of surveys. Sample size is still really important. Our model is pretty good at estimating the size distribution, even with those lower sample sizes, but the more information you have, the better the model is going to be able to estimate, and the more precise those estimates are going to be. And then finally, really the only problem is that it requires some prior estimate of detection on the line. And so we do suggest that you use some other kind of method to estimate that ahead of time. We're developing enhanced line transect distance surveys that involve intensive searches. We're still working on that. But we still think that this could be a potentially really powerful tool for management of this species. And if anybody is interested in the data or would like help analyzing their own set, I do have some R code, and I'm happy to share that with everyone. And so I'd just like to thank everybody who gave me funding, let me walk around on their land, and my lab mates for listening to me mumble in the car for the ride down here. So thank you.